Okay, so today we are going to start our conjugation and pericyclic reactions unit. Now for this unit, we're going to split it into two parts. We're going to do conjugation today, and we're going to do the reactions in the next video. And that's for the simple reason that conjugation allows us to dive deep into the structure. And you might say, I've heard of conjugation, I know about it, but we're going to really get down to why conjugation adds stability, and we're going to probe that very deeply in a conceptual way. So make sure we want to let that marinate while you prepare to start using and take advantage of that structural understanding to predict a very difficult outcome in a reaction with stereo and regiochemistry that is dictated by the structure. So we're going to give due diligence to the structure today and the structural implications of a conjugation and the reactions thereof. Now, to get your feet wet, we're going to, I'm going to ask you to do a warm-up, and so that's going to be attempted before you watch the rest of the lecture. So give it a try. You will have the opportunity to check your answers separately. I'm not going to reveal them in this video, though, because I want you to really think about it. So you're going to draw and name all acyclic isomers. Don't forget stereoisomers, so constitutional and stereo, of C5H8. So just as a hint, it might help to do the DUN, just because that would actually give you a much faster, let's see, I'll write that as a hint there so you remember. So don't forget the DUN, that'll give you a much faster kind of idea of how many pi bonds are in there. And since it's acyclic, don't consider rings. So the degrees of unsaturation, if you forgot that, that's something to review from 211. You will probably also want your model kits. So get those out so that you don't accidentally draw redundant ones, the duplicates, so no duplicates. And when I go over the answer with you, I'm going to ask you how many unique isomers you got. And we'll want to look at stereoisomers as well, which is where the model kits will really help. When you are done drawing, when you think you have all the isomers, feel free to check with friends and whatnot. I want you to find all the dienes in there and then label those dienes as either conjugated, cumulative, or isolated. And so let's just refresh what conjugated means in the sense of if you have a diene. If you have a diene, the 2 pi bonds in the diene, because there's 2 of them, right, will be separated by one sigma bond, and only one. I'm going to skip to the last definition because it's a very similar one to conjugated. Isolated diene would mean that the 2 pi bonds are separated by more than one sigma bond. Not separated, there we go, ated by, I'll say 2 or more sigma bonds. So in other words, you have to have the double, single, double pattern for it to be conjugated. If you have double, single, single, double, not conjugated. Lastly, you're going to probably, if you draw the isomers correctly, you're going to have some that are referred to as cumulative, which we've referred to as allenes in the past, if you took Organic 1 with me, aka allenes. So that means the pi bonds are actually connected with no sigma bond separating them. So pi bonds are adjacent. Okay, so hopefully that gives you enough momentum to get you started on that problem if you haven't done it already. So I do recommend you pause the video, give that a good try, and once you've given that some time, resume, and we're going to go on to the next page. And don't worry, like I said, we will check that later. Okay, so not to spoil it, so hopefully you've tried that. That's why I want you to try it. You might come up with these 2 examples. And so what we want to do is, throughout the rest of the section, is look, because we're about to do reactions with dienes, we want to look at some dienes and understand their relative energies, because that dictates how easy it is for a reaction to happen, right? So looking at these 2 dienes, which one would you label as conjugated versus isolated? Well, I hope you said the first one's conjugated because we have the pi bond, we have a sigma bond, then we have a pi bond. So this would be conjugated. And we can number 1, 2, 3, 4, 5, right? So this would be called a 1, 3 diene. Let's number this one. 1, 2, 3, 4, 5. Now notice that the pi bond pattern goes pi, sigma, sigma, pi. We are separated by more than, the two pi bonds are separated by more than one sigma bond. So what this means is it's not conjugated. These are isolated. And we refer to this, I'm not giving the full proper name, that's actually part of the previous problem, but in a generic term, if you see two pi bonds that have the pattern where we number it, and you arrive at number 1, and then you don't start the next pi bond until number 4, that's called a 1,4 diene. Regardless of whether the parent name is octane, octadiene, hexane, hexadiene, etc. Okay, so how can we answer this question, which is most stable? You might understand that conjugation adds stability. And this chapter is going to really focus on conjugation, which, by the way, comes from the Latin root con, with, and jugated comes from the word for join, so join with or join together. So it just means the pi bonds are actually joined together in that alternating double, single pattern. So we're going to explore the properties, and they have very unique properties of molecules that have conjugation and conjugated pi bonds. So to understand, before we start looking at properties, we're going to try to understand what makes them stable. And you might already know ahead of time the answer is, hey, conjugation always adds stability, but why? Why does it add stability? How do we know it adds stability? So where have we gotten proof that stability is actually added thanks to conjugation? One way to do this is to look at enthalpies of reaction, so the actual energetics. So you should have to have a little background from general chemistry to recall what enthalpy is. So remember, that's the heat of a reaction. And so just really crude overview, if we have a negative delta H, that means we have an exothermic reaction. And so obviously if it's not negative, it's not exothermic. But remember, it can get confusing when you have big numbers versus small numbers, negative sign versus small sign. But the idea is to think more negative, okay, means there's more heat given off. So more heat released for that reaction. So sometimes it's also called heat of reaction, right? So delta H. So we're going to look at the heats of reaction for various alkenes. And that could give us information about how stable they were to begin with, right? So first we're going to use hydrogenation as our comparison. And we're going to start with a single alkene. So it's not even a diene. So this is just an alkene. So it's not a diene. And then we'll compare it to a diene. So if you take this alkene and you add H2 to it, so this is also a good review for common reaction we do. You add H across the pi bond, and we do that in the presence of palladium catalyst. The enthalpy of reaction is negative 30 kcals per mole. So it's an exothermic reaction, and this would be called the heat of hydrogenation. So it's the heat for that reaction. So it's a hydrogenation reaction, so it's the heat of hydrogenation. So since it's negative, it releases heat, right? Okay, let's see what happens. And remember, I'm using units of kcals per mole. Some books might use kilojoules or something else. So what you want to keep in mind if you're comparing other sources is to just look at relative values. All right, so now we're not going to go through and calculate them all. We're going to use them as consequences to establish trends. All right, so let's do a diene. And which diene are we going to do? 1, 2, 3, 4, 5. We're going to do a 1,4 diene. So that was one we had the question about before. Because we have two pi bonds, we need 2 moles of H2 in the presence of palladium to fully get it to the same exact alkane. So that's the pentane, right? So if we want to reach the same one, a good prediction, I mean, it's simple, we have twice as much that we need to react, then I'd say, okay, well, 2 times negative 30 kcals per mole would give me negative 60 kcals per mole. And because I'm using previously established data to predict something that maybe is unknown, then I would call this my theoretical value. Let's compare that with what is known about this reaction. It's been done experimentally, the delta H. So I'm going to say theoretical delta H. I'll even put that here just to be a little extra clear, delta H theo. Experimental delta H. So, oops, I switched to eraser. Experimental. Not far off, negative 61 kcals per mole. Remember, this isn't linearly related, so one makes a difference, but it's close enough that that's a decent approximation. So what does that mean? It was not 30, it was 60. It was double. It releases more heat, right? It released more heat because there was more to react. All right, let's try the other dyne, see what's different about it. 1, 2, 3, 4, 5. We're going to try the 1, 3 dyne. Now, our calculations that we would do don't account for any regio differences, right? So any constitutional isomers, we're using the same bonds. We're still actually reducing 2 pi bonds. So my predictive value, so in other words, my theoretical delta H, I'm just going to get that situated, would be the same, 2 times 30, right? I'll just put even similar to, because we already know that the 2 of the pi bonds in the previous one made it negative 61. So I'll say it's about negative 60 kcals per mole. Maybe even it's 61. So it's a good guess because we know about that one. We've already discussed it. Well, it turns out the actual delta H is negative 54. And remember I said that this is actually a bigger difference than you think. It's not just, hey, it was close enough. I kind of tolerated 1 off, but 6 off is quite a big difference because 1.4 kcals per mole mathematically translates to about 1 order of magnitude at room temperature. So this is really actually a big difference. So I'm going to say, no, it does not match my prediction. How can we interpret this result? So I'll put exclamation here. So how would we describe the heat it's releasing? Negative 54 versus negative 60 kcals per mole. We could say it's releasing less heat. Negative 54 is releasing less heat than negative 60. Okay, what does that mean? That means that to begin with, which one's more stable? The one that releases more heat or the one that releases less heat? Definitely the one that releases less heat. So therefore, more stable to begin with. Okay, so that was our conjugated 1,3 dyne. We have one experiment so far, one parameter to tell us that conjugated dynes are more stable. So if you take, in other words, you take a 1,3 dyne and a 1,4 dyne, you do the same reaction on them. The 1,3 dyne releases less heat than the 1,4 dyne, meaning that that's a clue that the 1,3 dyne is more stable. And the difference between them is that the 1,3 dyne is conjugated. Okay, so let's see how we can, I really like plots because they, say picture's worth 1,000 words, same with a graph or a plot. So let's kind of represent this pictorially. Let's focus on the 2 dynes now that we know that those are really what we're trying to get to. And let's use our baseline. So remember, this is relative. Our baseline is going to be the pentane, the reduced product. So how far away were we energetically from the pentane? So I'm going to draw these in. So we're about 54 for the 1,3. So I'll put that one here. And we're at 60 for the 1,4. So that was this guy. And then this one was 1,3. So let me write that in, the 1,4 pentadiene. And that's 1,3 pentadiene. And then if we want to illustrate the energy difference, you can see we have less heat released in the conjugated system. So it comes down to conjugated versus isolated. It started at lower energy because this one was more stable. Okay, so this is summarizing what we talked about on the previous page, but using a picture, in other words, to do it. So I'll write out my conclusion right here. The relative energy of those two. 1,3 pentadiene is more stable than 1,4 pentadiene. Okay, so that's the conclusion. I'm just going to, kind of drive it home with the fact that the 1,4 is an isolated alkenes, or dienes, I should say, is less stable than a conjugated diene. Don't really like how that letters turn out. Conjugated diene. Okay, so if we're looking at stability, isolated dienes are less stable than conjugated dienes. So how did we know that? Their enthalpy of their reaction told us that. Now let's explore, since we know that the conjugated diene is particularly stable, we're going to explore properties of conjugated dienes. First, we're going to look at conformation. So this might be giving you a clue that they're pretty important functional groups, conjugated dienes. So they're going to play a big role for this chapter. So we're going to start looking at rotation. What does rotation mean? Newman projections, model kits. Okay, so dust off your model kits, and you'll probably want to build this. Feel free to pause the video, and you're going to build, instead of the pentadiene, the butadiene. So 1,3 butadiene. It also could be called buta-1,3-diene. You could put the number right before the ene. So it's going to look like this when you're done. 1, 2, 3, 4. Pi bond starts at 1 and goes to 2. Sigma bond, pi bond at 3 to 4. So we're going to do Newman projection down the only single bond, the sigma bond, in the carbon framework, which is right at the middle between carbons 2 and 3. So I'm going to number these. And then we're going to, and it's going to look a little funny because Newman projections were usually between two carbons that were sp3 hybridized. These are sp2 hybridized, so we don't see a third group coming off of our Newman. We have 3 total, but 1 is the bond going into the page. So it's going to look like a line only coming down. So what I want to do is start at 0, dihedral angle, which I'm going to refer to the dihedral angle of the 2 biggest groups. So once I'm looking down number 2, I can see my 2 big groups are the CH2s right here. So I'm going to draw on my H's because, so in other words, my eye, let's see, my eyes are technically hazel, so the closest thing to that is the green, but I need to like mix it with brown or something to get there, but hopefully you get the idea. So my eye is there. Use whatever eye color you have for that. And then we are going to look at what else is attached there. So remember that there's also an H on the 2 and 3 carbon. There's H's here. When you build your model, everything's going to be filled in. But notice that, so there's my head where the eye is. There's going to be H above my head here and the CH2 below my head. And if I start off with them opposite, it looks like this. All right, so if my eye is looking down there, I'm like this, and I see the H above my head, the CH2 below, and this is opposite. But my graph tells me to start at 0, which means the CH2s right here and here are going to rotate down. So the side, it looks like that, but when I look at the Newman, it's going to look like this. So how does that Newman look? It's going to look a little funny, but we can do it. So that means I have CH2 pointing down. All right, and here's my carbon, and that's me carbon 2. This is carbon 1. And then behind carbon 2 is carbon 3. That's part of the Newman projection. And then carbon 3 has the CH2 pointing down and the H going back up. So 2 has this H, 3 has this H, and then we have these CH2s here. So carbon 4. So this is 0 degrees. They're eclipsed. Let's just skip to 90. So what I'm going to do is we could choose what we want to do. Keep the front the same or the back. Let's rotate the back. So if it's my eye, I'm going to try to make it look like we're looking at the same thing. If I keep the front the same, I've rotated 90 degrees either way, it doesn't matter. That just means they're not going to be eclipsed anymore, they're going to be staggered. Okay, so let's just rotate it. Let's bring it up to our right. So I'll skip to 90 because I'm just going to sketch a rough plot for this purpose. And so we have C, I'm keeping the front the same, but I am rotating it so that they're staggered 90 degrees to each other. And just to keep track, I'll keep the numbering up. 1, 2, 3, 4. All right, so there's 90. And now let's skip all the way to 180. So that means they're opposite again. That's actually how they're drawn originally at the top here. So 180. I'm going to keep the front the same to keep it simple. But remember, the back's going to be opposite now. Now that CH2 is up here. And of course, it has to be offset slightly, even though in the real Newman that I'm looking at, they're perfectly superimposed. That's just almost impossible to draw. So I've got it kind of coming down like that. Keep my numbering up just so I can keep track. There's my 4 carbons. All right, now let's establish our, I'm gonna also do what I did before and label it. So this is staggered, and this is eclipsed. Now this is your prediction. So this means based on what you knew from 211. What we learned in 211 is that eclipsed is higher energy than staggered. I think I probably put this down too low. There we go. Eclipsed is higher energy than staggered. So let's let staggered be the lowest energy. I'm going to use green for my energy levels. And so I'm just arbitrarily going to say, let's let it be the minimum. Here's my energy for staggered. Because remember, this is relative. All right, so now I have 2 eclipsed to decide from. Those are higher energy, usually according to 212 knowledge, right? I think you have the feeling I'm going to be duping you, but I'm not really trying to. I'm trying to use prior knowledge to get to new knowledge. Okay, so staggered we predict should be low, and it usually is. Eclipse we predict should be high energy. Of the 2, which eclipsed is higher? The eclipse where the 2 big groups are coplanar. So let's write that word out, remember? Coplanar, the 2 CH2s are coplanar, or anti-coplanar, so they're opposite each other. Well, certainly I hope you say anti is lower energy, so let's just arbitrarily say, okay, if we make this a maximum, it's this high, but this one would be higher. So this is the highest energy, least stable. So this is the lowest energy. Okay, so based on sterics alone, this would be the right prediction, because that's what our 211 knowledge told us with Newman projections. So it's based on sterics. Let's see what the real drumroll diagram is. Actually, I didn't connect my dots. That's the fun part. Let's do that. Whee! So we see the shape looks something like that. I'm pulling up the next one. Look at this. Does that match? It doesn't really match, does it? So I'm going to label these just so we can track them. So this is eclipsed coplanar. This is anti-coplanar. And this was staggered. So we kind of had a similar result with our 2 extremes. Between the 2 eclipsed, we made the right call that coplanar is less stable, see higher energy, than anti-coplanar. So that agrees with us. However, we made the wrong call with staggered. Staggered actually turns out to be higher energy for dienes. Why is that? The answer is going to come back to one of the titles of this chapter. Oops, sorry, I didn't mean to move that. Okay, let's summarize this right now. 1, the diagram told us, put that down, eclipsed dienes are lower energy are more stable, lower energy, low E, than staggered. I'm going to put exclamation point because that's a surprise, right? Eclipsed is never usually more stable than staggered. But you never say never. It's always sterics versus electronics. In this case, we're going to see that the sterics predicted one thing, but since we didn't discuss electronics, that's going to be a whole other issue. Number 2, what else can we conclude? We've been saying this out loud. Between the two eclipsed versions, the CH2's anti-coplanar, so it's the last scenario, is more stable than syn-coplanar. Now that's expected, so I'll write as expected. Did not write anti-coplanar here. There we go. Okay. So we need to explore this more. What is going on with preferring eclipsed versus staggered? In other words, planar. Dienes are planar. But also, we're not surprised by the fact that what we call the S-trans diene, where they're opposite sides of the single bond, is more stable than S-cis, because look at those are close to each other. So that's not a surprise. But what was a surprise is that this, sterically speaking, something else is going on. So sterics would obviously say this is the most stable, but it's not. So electronics must be telling us, and that electronic effect is conjugation. Yep, so we had the answer at the title of the chapter, but how does a staggered conformation disrupt conjugation? So in other words, what this is basically telling us is this is conjugated. This is conjugated. That is not conjugated. It's harder to keep it conjugate. Remember the requirement of conjugation? You have to have all p orbitals, and remember they overlap side to side. They have to be parallel. So if you take a parallel p orbital and rotate it 90, it's not parallel anymore. It's not worth disrupting the conjugation in order to achieve more room for sterics, as we see in the energy profile. Okay, so keep that in mind. We're going to keep them planar. So the groups are in the same plane. The two alkenes stay in the same plane, even if it means they're more sterically hindered. All right, so I'm going to write that down here. Rotating dienes out of plane. And we say that so much because so many things need to be in plane or out of plane. There's a common abbreviation, OOP, out of plane, is not favored because it disrupts conjugation. Okay. All right, so if we are right about that, that means it's hard to rotate around the single bond. Okay, if you were in 211, you might say, well, maybe these have conjugation because they have resonance. They're intricately related, right? There's no way to separate that. We can draw resonance structures in which we can delocalize the pi bond to actually sometimes be in the middle here. So how does that look? So that means we have this pi bond to start with, we can do this resonance structure. Now, is that a preferred one? No, because we're making what's called a Zwitterion, a charged version, charge contributor. So we have a lone pair there. And I will just stop there. But what I'm trying to show is that not which is the major, the fact that it's possible to delocalize them. Since it's possible to delocalize them, that means this will have some pi bond character. So if I draw the hybrid, so remember resonance hybrids, when you draw different resonance contributors, you look at the ones you've drawn. So I'm just going to say of these two, would look like this. You always keep the sigma bond framework the same. Put the deltas where there's sometimes charge. So notice there's charge on the left species, but not on the right. So it gets a delta plus. Partial charge on the far right carbon, because it's not charged in both places. Pi bonds are not fixed, but there's spread throughout. So notice that we have pi bond character on all of the carbon-carbon bonds, which means that if another way to look at our model is to say, well, is this true? Even though this is a Zwitterion, and we wouldn't like to think of that as a good contributor, how could we see if the resonance really was happening? Well, so there's something we know about pi bonds. We know that the bond length of a pi bond is shorter than a single bond. So if we were to measure the pi bond here, and we said, well, there's resonance, that means there's some pi character. It's not always a pi bond, like here it's a pi bond, but here it's drawn as a sigma bond. So this has some double bond character. If it has double bond character, that means it's not entirely described with the same parameters as a single bond, which means it should not have the exact same bond length. Remember, the bond length's reported in angstroms. That's 10 to the minus 10 meters. Just because it gives much nicer numbers than having to write exponents. So if we say, okay, I believe there's resonance, even if it's the small contributor, it's there nonetheless. That means the bond length, we're talking about this bond right here, is going to be somewhere between 1.54 angstroms, we'll call it X, and 1.33 angstroms. The true bond length, here we go, 1.4, yes, 8 angstroms, we were right. So in other words, it's neither a true match with a isolated pi bond or a sigma bond. It has pi bond character since it's shorter than a normal sigma bond, right? So sigma pi, and this one is a sigma with pi bond character because of that resonance hybrid. Whew! So this is all some old stuff. We've talked about bond length before, but it's interesting to see how it can prove whether or not we expect to see resonance. So we saw that sterics did not tell us what conformation was most stable for our alkenes, right? Our dienes. So that implies that there's a lot at play with the electronics. The electronics is the reason if sterics is not. So in other words, when we're at 90 degrees, even though that should be more stable, it was less stable. Sterically, it should be more stable. Electronically, it's clearly not as stable. Why do I know that? Because it had the worst energy value, right? It wasn't as stable. So how do we find out the answer to what's going on electronically? You got to dig into what's going on with the orbital level. So we're going to do a quick refresher on molecular orbital theory. This is covered way back in 101. I'm going to assume most of you don't remember it. But if you want to go deeper than this one-page review, you'll need to go open your 101 book and kind of dive into a whole chapter dedicated to it. I'm hoping that this will be enough for us to go on and it'll kind of spark some memories. So remember, first of all, some basics. There are 4 quantum numbers to describe where an electron is, and we're going to refer to them. So we need to know those quantum numbers. So n is our principal quantum number, principal quantum. Why do we need that? That tells us the energy level, which is related to the distance it is from the nucleus. So distance from nucleus. All right, L is our orbital angular momentum quantum number. Helps us know about the shape of the orbitals, right? Angular momentum quantum number. M sub L is our magnetic quantum number. And M sub S is the spin. And we've talked about that with NMR before. So that describes the spin. So no two electrons can have the same 4 quantum numbers. They each have their unique combination. Let's see, what else might I want to say? Oh yeah, the allowed values of N. So, and also you have levels 1, 2, 3, so there's these integer values. And then L is allowed to start at 0. So in other words, N minus 1. So N equals 1, 2, etc. And L is allowed to be 0, 1, 2, ... N minus 1. Okay, so we're also going to discuss nodes. That's the space where the probability of finding an electron is 0. Okay, so that's where orbital, part of the orbital where probability of finding an electron is 0. So mathematically, nodes are equal to N minus 1. So number of nodes equals N minus 1. We're going to be concerned with what we call the frontier orbitals. So the frontier orbitals, which is way down here, are the HOMO and LUMO. So I'll define those. HOMO and LUMO. Why are we concerned with frontier orbitals? Well, where do reactions happen? Are reactions going to happen way deep at the core electrons? No, they're going to be at the highest levels, the ones that are the easiest to pluck off. So so-called frontier orbitals. So the frontier orbitals, the two that are involved in reactions, are the HOMO level and the LUMO level. HOMO stands for highest occupied molecular orbital. So what does that mean? The highest one in energy that still has electrons, it's occupied. In other words, it's ready to react. It's the highest energy one with an electron ready to give an electron to something, usually maybe a LUMO, an empty orbital. So that's the electron that's ready to go. The LUMO, let's do this in a color. So I should have done that. Highest occupied molecular orbital. L-O, oh, I have a typo there. U-N, unoccupied. M-O, LUMO. So the LUMO is the lowest unoccupied. So you start looking at the energy levels from the top. The highest one that still has an electron in it is the HOMO. Then you go up a level, because after that, if we're trying to look for the unoccupied one, so that'll be the next level up, hopefully, then above the HOMO, right? And that's where the electron is, where the electron could go, the next level. It's unoccupied, so it's empty. All right, so in other words, another way to say lowest unoccupied molecular orbital is to say the first empty orbital that is capable of accepting an electron. Okay, so when everything is in its ground state, i.e. lowest energy configuration, the LUMO's empty, the HOMO is filled at least partially, but in an excited state, you can promote an electron from the HOMO to the LUMO. So it's a higher energy conformation if you're in an excited state. How do you do that? You had to go up in energy level. So it had to absorb energy. It could have been energy from light, heat, different sources, right? So anything that can give it energy, usually it's higher. We call it thermodynamic pathway, heat driven, or photochemical pathway, light driven. So higher energy configuration. So in other words, you added energy. Okay, so I hope that rings a bell, because we need to put that all together, and you got it, an energy diagram. Okay, so let's use all of that terminology so that we can label and draw an energy diagram. What will the energy diagram be of? You guessed it, a dying. So that's the point of this chapter. Believe it or not, I think this is easier than the 101, what they're covering. They do all kinds of different starting Lewis structures. We are going to be doing dienes, trienes, etc. So polyenes, conjugated alkenes systems. And so we're going to look at specifically what it's like to look at those frontier molecular orbitals. So the HOMO and LUMO. We're going to label nodes, bonding orbitals, anti-bonding, that might ring a bell too, HOMO, LUMO, etc. Okay, so we're going to do 1,3-butadiene. So that looks like this. 1, 2, 3, 4, 1,3-butadiene. Okay, so what do we know about 1,3-butadiene? We know we have 2 pi bonds. How many pi electrons? So let's work that out. So this one has 2 pi bonds. How many total pi electrons? Well, per pi bond we have 2. Since we have 2 pi bonds, 2 times 2 is 4. So 4 pi electrons. Because we have to get to the bottom of that. That's where orbitals are, where electrons live, right? So we're looking at the pi system. So 2 pi bonds, so 4 pi electrons, 4 electrons in that pi system. In order to make those that dyene, we needed to use how many p orbitals? 1, 2, 3, 4. 4 p orbitals. Those are atomic orbitals, right? They're on each atom. But we're looking at we're discussing MO theory, molecular orbital theory. So those overlap to make 4 possible molecular orbitals. We call those pi orbitals to give us the pi bonds. Now, the 4 molecular orbitals come from the 4 p orbitals. So some students often say, how come my 4 p orbitals don't make one giant fat molecular orbital? And that's because of this other general chemistry concept that we introduced with how orbitals add together. And we brought it up before, but I'll bring it up again. LCAO, linear combination of atomic orbitals. Linear, so they follow that rule, combination of atomic orbitals. What does that mean? It's a fancy way of saying that orbitals are conserved. So the number of orbitals are conserved with any of these operations. So if you're trying to figure out how many hybrid orbitals you have, then and you started with 4 different atomic orbitals, you have to have 4 hybrid orbitals. Okay, so if you're going to have them all hybridized, you have to still end with the same number of orbitals when you're doing any of these operations. So orbitals are conserved. If you don't hybridize them all, then you have to have whatever, so let's say we had 2 hybrid orbitals, then you have to have 2 that are unhybridized. You have to add up to 4. So in this case, we started off, the same is true with these molecular orbitals. We start off with 4 p atomic orbitals. The different way those p orbitals can overlap gives us 4 possible molecular orbitals. So that number doesn't change. We don't combine it into one fat one with only one possibility. We consider all 4 possibilities. How do we know what those 4 possibilities are? This is the fun part. We're going to draw the energy diagram, and we will see the 4 possibilities kind of appear before us as we do that. So I'm going to take up this whole space here. Give myself lots of room. Okay, so this is increasing energy. And we are going to draw in the pictures of the p orbitals. So they're going to look at this. 1, 2, 3, 4. And because we're using 4 of them, we're going to use those to represent 4 molecular orbitals. So we need 3 more drawings. We need to have 4 total that we're going to fill out. And they're going to have different energy values, which is why it's okay to put one above the other. We just have to know which one's the highest and the lowest. So it's all relative energy. So we're just going to repeat this, and we'll color them in soon. Okay, so if we call this n equals 1, right? This is n equals 2, n equals 3, n equals 4. So let's call that the 4 energy levels that we have for those 4 molecular orbitals. Now, how many nodes would we have for this based on the mathematical formula? N minus 1, right? So at n equals 1, 1 minus 1 is 0 nodes. We'd have 1 node here, 2 nodes here, 3 nodes there. What does a node mean? Well, the p orbital itself has a node, the atomic p orbital, right there. So that's the shape of the p orbital represents a probability distribution of where you would find electrons. So it's really fat here, so that's a higher probability the electron is there. Because it comes to a single point here, that means there's 0 probability of finding an electron at that point in a p orbital. Okay, so with that in mind, that is a p orbital node. We're going to now talk about the molecular orbital, which means we're combining 4 p orbitals. What does the molecular orbital node look like? Well, we will not be able to draw that. It has to do with whether they are adding constructively or destructively when 2 waves. So this all boils down to quantum mechanics, which is using wave functions, which you may remember using some of that in physics. So when you add 2 waves constructively, you get a bigger value. If it's destructive, they cancel out. And so that's reflected in the shape drawn by the node. So wave functions that have been added constructively will give us a bigger probability of finding an electron there. Recall that no nodes means we have more stable, lower energy value. So what we're going to do now is try to find the nodes between the 4. So you have to color these. This is the fun part. We can make an adult coloring book out of this. So remember that each p orbital has kind of like these phases. So one side, we just represent that with a color. So one side would be like kind of shaded dark. We leave the other one unshaded. And so that means they're opposite phases. Some books might call it a plus and a minus. That just means they're different phases. We don't know which one was plus or minus. It doesn't matter. But if we let them overlap where they're all the same phase, okay, notice that they're all lined up with the same phase. That means there's actually no nodes. I think it becomes more clear when we see what one node looks like. So we could have equally colored it like this. Could have had half up dark, half down dark. Notice where we changed phase, right there. That's our one node. How could we get 2 nodes? That means we have to change phase twice. So we can color this. Let's try up dark. Let's change right away. But if we change each time, we're going to end up with 4 nodes. So let's not change, and change it again. Okay, that gave us 2 nodes. Here we changed. No node drawn here because we stayed the same, but we changed phases again. Notice they don't line up. They don't overlap constructively. So we're going to draw the second node there. 2 nodes. So those red dotted lines are the nodes in the molecular orbital. We're ignoring the original node in the atomic orbital once you get to a molecular orbital. Okay, so now we're going to try to draw 3 nodes, but I think you kind of arrive at that pretty easily. To do that, we have to go up, down, up, down, because that's the only combination we haven't really thought of yet, right? So change phase each time we go to the next one. So we've drawn 3 nodes. That's why it's the n-1. The n's don't count as a node. Okay, so these molecular orbitals have a name, a descriptor, a variable that's associated with them. So they're called psi, the Greek letter psi, which I know you're all doing right now. Psi. No, this is fun stuff. Psi 1 for the first energy level, psi 2, psi 3, psi 4. Okay, so let's fill in. After this part might be less familiar because we dove really deeper into what's going on with p orbitals in particular because they make the pi bonds. But this might start to look pretty familiar. We're going to fill in our electrons off-bow style, building up from the bottom. Okay, and so we always start from the bottom and we get to the top. How many electrons did we have again? We had 2 pi bonds. That means we have 2 pi electrons. So 4 now. And we always fill them up from the bottom, lowest energy first, opposite spin up, spin down, so opposite spins. That gives them the different unique quantum number, because remember they're in the same orbital, same energy level, however their spins are not the same. So that means they have their unique quantum number. You never have 2 of the same spin and the same energy level. Okay, that takes care of 2 electrons. I need 2 more. Okay, those are my occupied levels. So I'm going to draw a little line here. This might start to look familiar. And anything below that line is our bonding molecular orbital. So these are bonding. Bonding MO. Here's another bonding MO. Above that line, we're going to call these our anti-bonding, and they get a little asterisk, psi star 3, psi star 4, anti-bonding. So if they're occupying the bonding molecular orbitals, those encourage bonding, but if we were to promote them to a higher energy level, that is a step toward breaking the bond. That discourages bonding. So in other words, it's less stable, as it makes sense because it's higher energy. All right, so which ones are HOMO? HOMO means occupied, highest occupied. So you find the occupied levels. Psi 1 and psi 2 are occupied. The highest of the 2, the highest occupied, is psi 2. So that's our HOMO energy level. Where's our LUMO? Lowest unoccupied. Psi 3 and psi 4 are our 2 unoccupied levels. The lowest one of those is psi 3 star, so that is our LUMO. Okay, so this is the expected ground state. What would an excited state look like and what would it need? It would be exactly the same energy alignment relative, but we would have to add energy to change where the electrons are. So we'd have same energy levels, right? And that means that we'd be able to promote an electron out of the HOMO into the LUMO. And it doesn't matter if you'd put it spin up or spin down when they're not paired, but usually parallel spins are when they're not in the same exact shell, or is an indication that they are more stable. So, but you know, it's okay if you had put the down one and kept it down as you elevated it. So this has now been promoted to a higher energy level, the LUMO. The HOMO level is now missing 1 electron. And so we're going to call this our excited state. Doesn't stay there long, usually something happens. Reaction is progressing. Maybe it just absorbed some light and it's going to emit it later. So that is not necessarily a sign that a bond's going to break, but that's the progression toward breaking a bond. Okay, I recommend we accomplish what we want to do for 1,3-butadiene. I recommend you give yourself a little challenge and try the trying case. So maybe 1,3,5 hexatriene right there. It's a prompt. Give that a try. Feel free to share with me. It's fun to kind of work out all the nodes, especially. That's my favorite part. Okay, so the bonding orbitals, we're going to get back to those. Those are going to be really key for understanding reactions. But that's what it looks like when we zoom in on what the electrons are doing. Let's take a look at what's going on with the big picture. What happens when we have conjugated lone pairs? And how do we know how to conjugate lone pairs? So we've been spending a lot of time on dienes. Let's take a minute just to look at other types of conjugation. So here's heroin, and let's see if we can kind of justify what's going on here. So it says, what is the hybridization of nitrogen in heroin? What about the indicated oxygen? So that's a huge arrow to that oxygen, because there's more than one oxygen. So let's start with the nitrogen. I always say draw lone pairs when you have a heteroatom, because that can trip you up. So there's the oxygen lone pairs. Nitrogen's only missing one lone pair. Okay, so that hydrogen, when you count electron groups, we say, okay, we have 1, 2, 3, 4 electron groups, right? So it needs 4 hybrid orbitals. Right, so that's right. So geometry helps a lot. So 4 electron groups means you need 4 hybrid orbitals. And since we're in second row, you don't get to choose from very many, right? S and P, not even D. So if we have 4 orbitals being used and we're using all 4, then that means we have sp3. Okay, so sp3. Is it conjugated to anything? No, there's no pi bonds nearby. That's like the simple 211 case. It did come up now and then in 211. What happens if you can delocalize them? So these are not, this is a localized lone pair. Well, just for good measure, I've thrown in an example where it can be delocalized. So notice that this lone pair is adjacent to a pi bond. So that means that's one of the resonance patterns, right? So delocalized lone pair. So you got to be careful, because that means if it's delocalized, it must be in a p orbital. You can't turn that into a pi bond in the next resonance structure unless it's actually going to use a p orbital. You have to have the p orbital available for that. So must reserve p orbital for delocalization. So as usual, we still have those orbitals available. We have an s, p. We're in second row with oxygen. We have s and 3p atomic orbitals available to hybridize. But we have to reserve, I'm going to use it in green, this one, or any of them, doesn't matter, px, py, pz. We have to reserve one of them. It's off limits to be hybridized. Has to stay a pure p orbital in order to have delocalization. Why? What are we doing with this arrow? We're making a pi bond. Pi bonds require p orbitals. P orbitals cannot be an sp3 hybrid. So this stays out of the possibilities. How many other groups of electrons do we have? Circle in blue, we need one here. That's not invited to that party because I drew the arrow on the other one. This one is localized. It's because it's not participating in the resonance. Okay, so you can only delocalize one of them at a time. So there's that. That's one group. There's another electron group. There's another one. So we have, and then I'll keep this one in green. That's the one I'm just choosing to, I could have chosen the other one, but one of the 2 lone pairs is delocalized, the other one stays localized. So that means that there's 3 blue. Those 3 blue are how many hybrid orbitals I need. So what did I put in the circle? I put an s and 2 p's. So that oxygen is sp2 hybridized because one p orbital has been taken out of the listing as an option. So the hybridization of the O is sp2. Okay, so that's review, I hope. But that's kind of the point we got to in 211 with conjugation. So we would say that lone pair is conjugated to the pi bond because it can do resonance. So sometimes If you look through some old exams, you'll see questions like testing if you can recognize what's conjugated, what's not. What's the highest number of consecutive atoms conjugated in heroin? I'm going to give you the answer, kind of maybe pause here and give it a try, but I'll write it down right now, so you might want to pause, and then check your answers later to see if you can match it. Okay, so you should get 10 when you're done. Okay, so next concept, we're ready to use conjugation and study its effect on reactivity, and we're going to do that first with familiar reactions before we get to our new reaction in the next video. So in this reaction, we're bringing back the addition of HBr to a pi bond. This is a 211 reaction, so if you're not clear on that, go ahead and review it. But we're going to just do one equivalent. And we're going to explore which of the two pi bonds are going to be added to, or which carbon gets the bromine, in other words. Okay, so let's draw some outcomes. I think I'll do red and blue. Let's start with red. All right, so I'm going to take, let's see, I could just take this one and take an H. And so that's my mechanism. And let's draw the product that we get with that. But to do that, we kind of need a mechanism, right? So what does that look like? Oops, I don't have a pi bond. So I left this one alone. And where's that H going to go? That H is going to go where we'll get a more stable carbocation. So that means we're going to give that the H so that we can have a secondary carbocation instead of a primary one. And that has resonance. So this is actually secondary with resonance. And so let's do some resonance. So we could do this. Look at it, what resonance it has. I won't draw the H every time, but that is the new H from the HBr, the one that I bothered to draw in the first time. Okay, so now I'm going to put this in, and that gives us a primary carbocation with resonance. Okay, so we could have, I'm going to track that H just so we don't forget, because we are adding HBr. Okay, so that means we can add the bromine here, or we can add it here. And it didn't matter which pi bond I took. It matters which, because notice how they're similar. Terminal or one away from terminal. So I'm just starting with this one. So it doesn't matter which one I took, but what does matter is where the H goes. So if I put the H here, then the bromine's going to attack there, or there. So let's continue in red if it attacks this one. I'm just going to go ahead and draw the H since I'm going to do this again. So bromine, remember it's ready as a negative charge now, and it's going to attack. Oh, I could draw all the lone pairs for good measure. There we go. It's going to attack right there, and we will have this product when we're done. We'll have an alkene with a bromine on it, and I'm going to draw the H in simply because I want to see which one got how far away the Br is from the H. So if I number this, carbon 1, 2, 3, 4, I'd say this was the 1, 4, called addition, because we added to the pi bond, or adduct sometimes it's called. Addition. Okay, now let's do in blue. Let's say we took, you're probably saying, why in the world did you pick the worst resonance structure? Let's take a look. I'm going to do both, because we usually try to do that back in 211 when we're fully evaluating reactions, look at all possible paths. So let's do in blue this path. Let's say the bromine instead, or bromide, attacked the better carbocation, which it bloody well should if that's what you believe, right? But that's what we learned in 212. Let's draw that product, and I'll keep it in blue now just to distinguish that path as something different. So we have our H, which is the green H. We have our bromine adjacent to it, and we did not do our resonance yet. This is our green H. Let's label this 1, 2, 3, 4. Since the bromine and the H are at the 1, 2 position, and those are the new atoms, we call that a 1, 2 addition product. So these are the possible products. So 1, 2 addition or 1, 4. Okay, now what you might notice is that we can easily get caught up in the carbocation stability and forget the final product might be better with the worse carbocation. So notice that. Better carbocation went blue. The better carbocation went blue, and we got a monosubstituted alkene. Worse carbocation went to the red path, and we got a disubstituted alkene, right? And we've learned that disubstituted alkenes, Zaitsev's rule, are favored, right? So more substituted alkenes are favored. I'm gonna write that down. We're prompted as long as we go, so I'll fill that in, but we might go back and label it just to be extra clear. Okay, so the one that's formed the fastest, I'm using this word on purpose, fastest, would be the one that's easier to form. Okay, the one that's easier to form is the one that has the path of least resistance, lower activation energy, more stable carbocation. So 1, 2 addition is faster. Because better carbocation always means lower activation energy. Okay, so we're going to call that product, because it's faster and easier to form, kinetic product. It's the fastest one. Doing it in blue. So this is our kinetic product. Kinetic, so it matches the color product. The most favorable we saw, the actual product that was better. So in other words, let's go back and illustrate that this was the better carbocation. However, this one is the more stable product because of Zaitsev's rule, right? So it's disubstituted alkene is better than monosubstituted. I'll just abbreviate substituted with S-U-B-T-S-T. I do that a lot because it's common and we're using it a lot. The more stable product is this one that I just labeled, the 1,4 product. So I'm doing that in red. So we call the more stable one the thermodynamic product. So it may have had the tougher route, higher activation energy, but it was worth it for the gain you got at the end. So why was it more stable? The more substituted alkene. I'm going to invoke our old friend Zaitsev. Oops, alkene. I think I'm getting cut off there. There we go. Zaitsev's rule, right? Okay, so that makes it tricky. One is easier to form, but one's better to form. Who forms? That's going to be the question. We're going to want to know how to tailor reaction conditions to control one over the other. And the good news is you just have to fix what's over the arrow to get what, add some extra detail to what's over the arrow to favor one path over the other. Okay, so things that favor the thermodynamic product are reversible reactions. So I'm going to write red because it's thermodynamic, and that was our red path. So reversible reactions. So in other words, equilibrium conditions. So you encourage equilibrium because if you think about it, you're almost letting the reaction have a do-over. if you have an equilibrium as opposed to unidirectional. So if you do an equilibrium, it has a do-over and keeps going until it settles into what we call thermodynamic well, so lower energy potential. And when it does that, it's less likely to go back. So remember that equilibrium constant will be different than if it's a less stable product, right? So you want to favor equilibrium or encourage equilibrium conditions because those reactions are slower. And they do what we sometimes refer to as self-checking, kind of check themselves, say, oh, if I do this carefully, I'm going to have a more stable product in the end, even if it's not the best thing right now. So it allows for self-checking. If you encourage equilibrium, usually that means it's like acid-base conditions, right? That's our favorite equilibrium examples. So e.g. base, acid. Other things that encourage the thermodynamic product to form is given in the name. The energy barrier is higher. To overcome a higher energy barrier, you need more energy added. That's added in the form of heat. So you just add more energy than needed to overcome both energy activations. So add enough delta, that's heat, remember, to overcome both activation energies. So not only the kinetic activation energy, which is going to be lower anyway, you want to overcome the thermodynamic activation energy. So just add way more heat, and that way you just overcome both of them. Okay, so, but what if we really want the kinetic product? I'm doing that in blue. There's a reason I picked those colors. Might become clear now. Red, hot. You need it to be hot. Blue, cool. So the kinetic product, low temperature is usually the key. Because that way, if it's only the first activation energy, the lowest one, which is its activation energy, is accessible. And then also avoid equilibrium. So instead, if you have to do acid-base, make sure it's a really strong acid or base, so it's encouraged to stay in one direction. Avoid equilibrium to slow down the reaction. You kind of want it to go so fast it doesn't know it picked the worst path, in other words. Okay, so that means you need very reactive starting materials. Let's superimpose these two like this. That was a lot of definitions. Once again, I love to have the picture, the energy profile, sums it all up with one unifying image. And so we're going to superimpose the blue path and the red path energetic profile. And I'm only going to do the step that's significant in that case. So hold on, let me get my, there we go. Axes drawn in. Okay, so I'm going to have my energy going up. I have my reaction progress. Okay, all starting materials will be the same level. This is a very generic one. I'm not going to make it specific to addition of HBr. This is supposed to be a generic template for all the important step that separates kinetic products from thermodynamic. So starting materials are always the same. Products are different. So if you have the kinetic product, that means you took the blue route in our specific example, but I'll make it blue in here for a genetic one. So product is P, but since I made it blue, I'm going to call it kinetic right there. And remember that if it's the thermodynamic product, it's lower energy, it's more stable. But the activation energy, so oftentimes the formation of the carbocation, whatever the transition state, the first transition state is, that distinguishes those two paths, the blue one is going to be lower. So let's call that EA kinetic. And the red one is higher, EA thermo. So let's connect those. I'm going to use red for my thermodynamic path. Goes up higher, higher activation energy, but settles on a more favored product. So if I want that product, I add lots of heat so that I overcome even the red activation energy. If I don't want that product, I keep it cold usually so that I only can overcome this energy barrier. Cold might even be negative degrees. It might be easy for the reaction to happen. Some ideas of heat for thermodynamics will say RT, room temperature. It's relative. So if you see two reactions side by side, one's room temperature, one's 0, then a degree Celsius, then you'll want to acknowledge that 0 is colder, right? So it's not a set temperature, it depends on the reaction. Okay, there's my blue path. Settles on a higher energy product, less favorable product, however, easier to form because I managed to get to the lower activation energy. Okay, so we will refer to that plot a lot. So we will want to be comfortable applying that to various reactions that have thermodynamic or kinetic control. Okay, we're not done with conceptual conjugation. This is an interesting biochemistry example. Conjugation can be important enough to dictate the protein conformation. So here is a polypeptide. And so what I want you to look at is kind of think about how it's a polypeptide structurally. So remember the primary structure of a protein is the amino acid sequence. And amino acids are formed with a carboxylic acid, which used to be a carbonyl here, that made an amide bond. So a peptide linkage right there. So this would be one amino acid. This would be another one. This would be another one. So there's 3 amino acid residues in this polypeptide backbone. These R groups would be their side chains. And let's identify the bonds in the backbone that have restricted rotation. Well, what do we know about rotation? We know that if we have a pi bond, it can't rotate, but if we have a sigma bond, it can. So we're going to ignore pi bonds, and we're only looking at the backbone. Okay, so what would cause restricted rotation? Anything with pi bond character. Notice I said character. It doesn't even have to be a total pi bond. So a pi bond has no rotation, but if it even has pi bond character, it will have less rotation because it has that property of being like a pi bond character. So in other words, what sigma bonds in the backbone can have pi bond character? So in other words, can we rotate here? Sure, why not? There's no reason for it to have pi bond character because even though I have a lone pair here, I don't see any way for it to be conjugated to allow for pi bond character. So remember, when we have conjugation, we have pi bond character. Can we rotate? My pen is not happy. I'm going to give it a second to respond. There I go. I was doing too much at once. Can we rotate here around that bond? Sure. These 2 atoms are not conjugated to each other. Now think carefully about the next one. The amide peptide linkage. Notice that you could do this move. Delocalize the electrons. Means that the hybrid will have a partial pi bond. So that means this is not going to rotate. So when I do that, I'm going to put an X through it. Restricted rotation. So no / minimal. It's hard to rotate. The energy barrier to rotate that is hard. Due to conjugation. So when you go on to biochemistry, you'll probably just explore protein conformations. And when you get down to the bottom of it, it comes down to this organic structure where we can explain it with conjugation, where we have degrees of freedom here to rotate. Not here. This doesn't count as a degree of freedom. So when we consider all the different ways this protein or shapes it can adopt, we are not going to consider this rotation. So that's restricted rotation. So is there a color I haven't used? I'll keep with green. So this has restricted rotation. That'll stay planar. Do we have any more amide linkages? Yes. This one stays planar. Okay, so watch out for that when you have proteins that comes back. This is a continuous concept that builds into other classes. So another really fun application that we get to cover now with conjugation is color. And that's exciting, especially in organic, because in the lab, we just work with white solid, after colorless oil, maybe colorless liquid, back to white solid. Very few organic compounds are colored unless they have a particular property. Usually it's extended conjugation. So quite a bit of conjugation. So in order to understand why we have the color, we have to go back again to our orbital diagram. It comes down to electronics. And I'm not going to go through and write all the phases of all the orbital cartoons and everything in again this time, because we did that once already in this video. But I'm just going to get right to the punchline, which is what's going on with the energy diagram of the electron configuration. So notice, because we have 4 pi electrons here, so I'm intentionally picking the same example so that we don't have to spend too much time deriving that. So that means we must have 4 molecular orbitals, psi1, psi2, psi3, psi4, and that those 4 electrons are going to occupy the lowest energy levels first. So pair, spin up, spin down, spin up, spin down, which means we can say, okay, here's our line separating the homos and the lumos and the anti-bonding from the bonding. So I'll put anti-bonding here, MOs, and below that line are bonding MOs. All right, so then we have the energy difference that we could think about between the HOMO and the LUMO. So let's label the HOMO and LUMO. HOMO is the occupied one that's the highest. LUMO is the unoccupied one that's the lowest. So the difference between the HOMO and the LUMO has a discrete delta E value. That is the energy needed to excite an electron into the next level. So this would be its ground state. Let's get it to the excited state. So that would mean we have the same energy levels. So we'll sketch those out real quick. Psi1, Psi2, Psi3, Psi4, sigma star, there we go. All right, so we had the lowest level left alone, but from the HOMO, one was promoted to the LUMO. And this is called a pi to pi star. So we went from one pi molecular orbital that was bonding to an anti-bonding one. And this is called a transition, pi to pi star transition. And it's observed in conjugated pi systems. Okay, so when it gets promoted, it has to respond. So whatever's characteristic to that energy difference, it will eventually relax back down and have to give off and emit that energy value, that same exact energy value, whatever it was to get there, that's what it lets go. That's how fireworks work, by the way. It excites them to the next level, and the level it relaxes back down to happens to be the exact level of the color that you wanted to see. So that's how you could design the fireworks to be that color. Okay, so one trend that's kind of interesting here, though, is that as you increase conjugation, you're lowering energy values, right? And you actually get them closer together because they're all lowering. So the delta E gets smaller. So if you increase conjugation, it is equating to a decrease in the delta E. And so now we're getting into what happens when the energy is lower. And we're going to relate energy to wavelength now. So in order to do that, we're going to look at the color wheel. So just a few reminders of energy. So if you have energy, you can relate it to wavelength, hc over lambda. So energy is inversely proportional to wavelength. So in other words, if you have, the conclusion we made on the previous slide was if the increase conjugation, we decrease energy, that means we increase wavelength. Just want to keep it all straight. Okay, so how does this work in the color? We drew a wheel on purpose. You might remember also from the electromagnetic spectrum, we get Roy G. Biv, where on the R side, if we continue, we get IR. On the other side of the violet side, we get ultraviolet. That's important. We talk about that spectrum a lot with spectroscopy. And we know that ultraviolet, if nothing else, you can remember that it's bad for your skin. It must be high energy, right? So this is the higher energy end. That means, inversely for the wavelength, it's a low wavelength. Usually it's around 200 nanometers, just for reference. IR is the opposite. So low energy, high wavelength, and we're going up to past 800 nanometers there. So red ends around 800 nanometers. Let's call it about 900 nanometers. So this would be about 800 nanometers. And violet's around 400 nanometers. This would be like 900 to 1,000 usually. Okay, so Roy G. Biv is our visible part of the light spectrum. So that's where we see color. And if you rearrange the visible light spectrum into a color wheel, that you might have done some of this in physics, by the way, or maybe general chemistry, you get the complementary colors. So in other words, we follow sort of that subtractive model to predict what color we'll see. So if orange is, well, in other words, let's say white light just hits an object. It'll absorb the light. So light is h nu, right? So that's also a frequency relationship. Let's write that down because we often use h nu as an abbreviation. Light absorbs, is absorbed, we call that h nu, absorbed at what we call the lambda max. The rest of the light essentially bounces off, and we see the kind of the remaining color. So whatever it absorbs, we can essentially look at the complementary color to see what we actually get to observe. So there's if orange is absorbed, we see blue. If blue is absorbed, we see pretty much orange because blue is removed. If blue is removed, we don't really see purple or green. So the net effect is the orange, right? Okay, so just for some real life examples of difference in absorption and observed colors, let's look at these right here. 1,3-butadiene we've been following through as an example this whole section. So it turns out, yes, it's conjugated. Yes, that means it has lower energy. Not low enough to hit the visible range yet. Remember, UV is higher energy, it's still in the UV range. If a sample is still absorbing in the UV range, we don't see color, it looks white. That's how most organic molecules are. And look at even conjugated with 6 atoms. So we've increased the conjugation. Sure, it's lower energy than the previous one. We're still in the UV range. It takes a while. Styrene is highly conjugated. Polystyrene is the, you know, what your coffee cups are made out of, the disposable ones anyway. Still white. It takes a lot of conjugation to finally see some color. So retinol, which absorbs energy in the purple range. But if you look at the complementary color, so you'll actually want to sketch a color wheel and to solve these sorts of problems. And so if you don't have it left on your page, I would just start writing Roy G. Biv out like this. Roy G. B. and then a P. Indigo and violet are really purple, right? Because I mean, what is indigo? But it makes your color wheel easier too. So then you just kind of cross these. That way you could see their matches. So if it absorbs purple, then we see yellow. So retinol, vitamin A, has more of a yellow color. Retinal, and so these are biorelevant, found in carrots, right? So some of these, and they have a lot to do with the chemistry of vision as well. And so you can read up on that. It's pretty interesting. But yeah, they are related to each other by simple oxidation. So notice that we went from an alcohol to the aldehyde, and an enzyme does that, but not PCC. No PCC in the body. Although if we wanted to do it in the lab, yes, we would use PCC. Okay, so if it absorbs blue, that means we're going to see orange. Lycopene found in tomatoes, therefore red, right? Very highly conjugated, but absorbs the green in order for us to see the red. So it takes away the green, and then we see the red. Red appears. So this is the apparent color, what we can see. Appears red, absorbs that color, appears this color. So we can predict what color something should be when we have the bulk, enough of it to see a sample, using a type of spectroscopy called UV-vis spectroscopy. So it's actually really simple. It's even simpler than IR in terms of interpretation. It's an absorbance plot, similar to how IR is, only you can see the peaks go up instead of coming down. Absorbance, because we're often looking at transmittance in IR. And it's absorbance versus lambda, so the wavelength of the light. And just the only thing that's really relevant that comes up in some problems is that we like to see signals. So if it is absorbing in the UV or visible region, so that's what's plotted here, somewhere from 200 nanometers up to 800 or beyond to get to visible. So notice it's UV to vis, right? And so if we want to see if anything absorbs in the UV or visible range, if it absorbs in UV, then we know it's going to be white. If it absorbs anything invisible, then it might suggest what color it could be. So how do we know what it would do? We would look at where its absorption is, the lambda max. So it might look something like that, and you would trace that down to whatever value that is on the x-axis. That's called the lambda max. I could approximate, I'm a little more than halfway to 800 from 200. So let's see, I would say 400 would probably be here, 600 here, so it might be around 500. Yeah, so that would indicate visible range absorption, right? Okay, and we remember that lambda max is due to what we call the pi to pi star transition. That absorption of the energy to allow from a HOMO-LUMO transition. And then we can relax back down and we'll see the color. Okay, so that's UV-vis spectroscopy and the nature of conjugation from start to finish in terms of how it can change reactivity, how it can change shape, how it can change color. And what we're going to do next is study one of the biggest reactions, a carbon-carbon bond forming reaction, the Diels-Alder. So I'm going to stop here because this got deep. Review the orbitals and everything, and then we're going to continue with the rest of it next time. So I hope you enjoy practicing some problems with predicting colors, refreshing your HOMO-LUMO information, and then we'll pick up, and I can't wait to start Diels-Alder. It's a fun reaction.